Okay, let me remind you of the lemma for the closedness on the metric space we have justified last time. We have a metric space X with its metric D. And we have a subset A of the whole matrix space. Then the subset A is open if and only if its complement is closed. Yeah, this was the lemma for the closedness on the metric space we have justified last time. And then let me make some remark about this lemma. In a topological space, this lemma is used for the definition of closedness. In a topological space, X, this lemma is the definition of a closed set. The reason is because in the topological space we, in general we may not have what? The metrigon, right? Where the real number line is a special case of n-dimensional Euclidean space, and n-dimensional Euclidean space is a special case of metric space. And the metric space is a special case of topological space. And how did we define the closedness on the metric space? To define the closedness on the metric space, we have used what? Contact point, right? But to define the contact point, we didn't need what? Metric on the metric space, which the topological space doesn't have, right? So then, because the topological space does not have the metric on in general, there is no way to define the closeness on that general topological space using the contact point thing, something like. So we use this lemma as the definition of closeness on the general topological space. In other words, on a topological space X, on a general topological space X, a subset E is closed if its complement is open. Yeah. Oops. Any questions or any comments on this? Yeah. Okay, actually, then I will keep reminding you of this kind of diagram that tells you some relations between the spaces, okay? And n-dimensional Euclidean space is a special case of inner product space. And the inner product is a special case of normed space. And the normed space is a special case of metric space. And the normed space is also a special case of vector space you have studied in linear algebra. Yeah. And then later on, we can combine the metrics, the vector space and topological space, which is called topological vector space. So then that's a big picture for the diagram that tells us some relations between the spaces in analysis trend, analysis branch and linear algebra branch, and then those two branches are combined together afterwards in the functional analysis theory, which is called the topological vector space. Topological vector space. Then we have the following corollary, which is easily derived from our previous, justified stuff. Corollary. Let's let tau be a topology on a subset X. So then what I mean is, let's let a set X and tau, which is a collection of subsets of the whole set X, be a topological space. Then you remember that this tau is a collection of some subset of the whole large set X, right? Satisfying three rigorous conditions, right? Satisfying three rigorous conditions. And then we say that every subset in this tau collection is called an open set in the topological space, right? Yeah. If you have this topological space X with the tau collection, then what? Tau will be the collection of some subset of the whole large set X satisfying three rigorous conditions. That was the definition of a topological space. And then each subset in this tau topology, tau collection is called what? The open set on the topological space. Then, by the previous remark over here, okay? By the previous remark over here, okay? By the previous remark over here, we say that a subset E on the whole topological space X is closed if its complement is open, which means its complement is an element in that topological tau collection. That's what that means. Right. And that stands for the openness of E complement. Openness of E complement. Then what is the result of this corollary then? First of all, if you have an arbitrary collection of closed subsets on this topological space, then what? Their intersection is also closed. Their intersection is closed as well. If each E sub alpha is closed on this topological space, which means the complement of each E sub alpha is what? Is open, which is in the tau collection there. That's what that means. For all alpha in the index set gamma. For all alpha in that index set gamma. Then their intersection is closed as well. Intersection of E sub alphas. All of their intersection is also closed. Secondly, if you have finitely many closed subsets of the topological space X, and then their union is also closed. Their union is also closed. I believe you are already familiar with those properties. Closed set properties we have studied in what? On real number line in the real analysis last year, and then the same results are what? Naturally extended to the general topological space. We can easily write out their proofs. Well, take the complement of intersection of the closed sets E sub alphas. Then by the De Morgan's law, the complement of intersection is same as what? Union of each complement. But since each E sub alpha is closed, each complement of each E sub alpha is open. By the definition of closedness in the topological space, right? Each E sub alpha is closed, so complement of each E sub alpha is open. Then what happens to their unions? By the open set properties in the metric space or topological space, we have, that's by the definition of what? Definition of topological space. I believe this was the first condition on the topological space. If we take what? Arbitrary collection of what? Open sets in the tau collection, and then their union must be also what? In the tau collection, which must be open. That's what, right? Yeah. Okay. So the complement of this intersection is open, so then what must be happened to only complement? So what must be happened to their intersections of E sub alphas? By the definition of the closeness again, okay, intersection of the closed sets E sub alpha must be closed. Because there, its complement is open. The complement of intersection is open, so intersection is closed. Intersection of E sub alpha must be closed by the definition of closedness in the topological space. Yeah. So how about the second? How about the proof on the second? Let's use another De Morgan's law. Okay, we want to show union of those finitely many closed sets E sub i's is closed. For that purpose, let's look at its complement. Then by the De Morgan's law, its complement is same as what? Intersection of each complement. But by the definition of the closedness again, each E sub I is closed, so each complement of E sub I is open. Then how about their finite intersection? That must be also open. By the definition of what? The topological space again. I believe that's the second condition on the topological space here, right? If you have finitely many open sets in the tau topology, and then what? Their intersection is also open, which is in the collection of tau topology. So the complement of union, this finite union is open, so what? By the definition of the closedness, only finite union must be closed. That was what we have desired. So the arbitrary collection of closed sets is closed, and the union of finitely many closed sets is also closed. Yeah, those are the closed properties in the general topological space. Any questions or any comments on this? Then what's next? Closure, interior. You remember those terminologies we have studied in real analysis, right? What was the definition of the closure? What was the definition of interior? Please remind you of that. And then exactly same, the definitions for about the closure or the interior will be extended. Okay, extended to the metric space, Exactly same definitions about the closure and the interior in the real number line we have studied in the real analysis will be extended to what? This metric space theory. That's the definition. We have a metric space X with its metric D. And we have a subset E of the whole metric space X. And let's let E upper bar, which is called the closure of E. Closure of the original set E is defined by the set of all elements X in the metric space X, which is such that the point X is a contact point of the subset E. So, simply speaking, take the collection of all contact points of the subset E. Then, this collection is called the closure of the original set E, and it is denoted by E upper bar. Okay, the closure of E is the collection of all contact points of the subset E, original subset E. Yeah, here is the whole metric space X with D metrigon, and then I don't know how that metric space looks like. And on this metric space, we have a subset E. I don't know how that subset E looks like either. Then, what is its closure? Its closure is what? Closure is the collection of all the contact points of this subset E. Then what? How should it look here? Then must be everything interior and the boundary, right? Then must be everything for the union of interior and the boundary points. Intuitively. The collection of all contact points of the subset E. Okay? So that must be what? The union of every interior of E and the boundary point. So that's the kind of geometrical intuition. Yeah. How do we write this? Sequentially. A point X is a contact point of the subset E. Then how do you rewrite it sequentially? Yeah, this is the collection of all element X in the metric space X such that what? How do you rewrite this part over here? Sequentially here. Sequentially. Every point X in the whole metric space X such that there exists a sequence X of n. Okay, sequence X of n such that each term of the sequence X of n is in the subset E for all index natural number n, and the sequence X of n is converging to the point X. That's how we rewrite the definition of the closure of E, the subset E, sequentially. Actually, these two statements are equivalent, right? As we have proved last week, right? Yeah. X is a contact point of the subset E is equivalently what? Equivalently what? There is some sequence X of n in the subset E converging to the point X. Yeah. That's the definition of E closure. That's the definition of E closure, which is the collection of all contact points. Let's go one more step here then. How did we write it? That's the collection of all contact points of E. And, equivalently, yeah, this is the equivalent statement sequentially. Then how did we write it? The collection of all sequential limits on the subset E. That's what that means, equivalently, right? Take any convergence sequence in the subset E and take its limit, right? There are, if you have a subset E, I don't know how the subset E looks like. If you have a subset E, and then there are a lot of convergent sequences happened inside, right? There are a lot of convergent sequences, X of n's and Y of n's and Z of n's. There are a lot of convergent sequences in the subset E. The first sequence X of n is converging to some number X, and the second sequence Y of n converges to some other number, and take all those limits of convergent sequences in the subset E. That's what that is. The sequences must be inside E, not outside of E, right? Take any convergent sequence in E. Take any convergent sequence in where? In the set E. And then take all their limits. Take all their limits. That's the closure of the subset E. That's the closure of the subset E. Then we have 6 different the properties about the closure here, which is the next lemma. Yeah, first of all, the subset E is a subset of its closure. That's the first property about the closure of the subset E. Why is that true? I already showed the intuitive picture, right? That is true intuitively because what? If you have the whole metric space X and we have a subset E, then what? Actually, E closure is what? The collection of all contact points of the subset E, which means what? Which must be the union of all of its interior and the boundary points, right? So then, intuitively, that must be true. The subset E itself must be a part, what sub-collection of what? Its closure. That's pretty close, pretty clear intuitively, but how do we justify this clear thing, the intuition mathematically? If you take any point X in that subset E, then why don't you take the constant sequence X converging to itself, right? The left. x of n be the point x itself for all index number n. Each term of the sequence x of n is x itself. That's a constant sequence. So that's a sequence anyway. That's the sequence x of n is a sequence in the subset E, converging to what? Converging to the limit number. So then what does that mean? That means the limit x that sequence converges to is a what? Contact point of the subset E. Which means the number x, I don't know if it's really number, but that's a general metric space. It may not be, right? Yeah. Then the x the sequence converges to must be what? A contact point of E, which means what? The point x the sequence converges to must be what? In the closure of E. Yeah. We take any arbitrary point x in the subset E and then take the constant sequence x converging to itself. Then x is the limit of the sequence x of n in E. X is the limit of the sequence, constant sequence x of n in the subset E. Which means what? Which means x is a contact point of E. Which means the number atom. The x the sequence converges to must be in the closure of E by the definition of the closure. The second part of the lemma is if E is a subset of D and the larger set D is closed, then the result of the lemma is that what? Closure of E is also in the closed set D. If you take a closed set D containing E, that's how you interpret, right? If you take any closed set D containing E, then what must be happen? The closed set must contain what? E closure. Oh, sorry, I missed something before this lemma. Actually, I must prove, first one, before that, the lemma I have stated, then I must prove the closure of any subset E is closed. That's what we must prove first for the next one. Yeah. For any subset E, its closure is closed. Its closure is closed. Now, how do we prove this? How do we justify this fact? The closedness of E closure. Closedness of E closure. So we show that the E closure contains all of its contact point. By the definition of closedness, we prove that E closure contains all of its contact point. So for the purpose, let's let an element X be an arbitrary contact point of E closure. And then we show what? We show the contact point X is in E closure itself. So what I mean is we show any arbitrary contact point of E closure is in E closure. So which means we show that what? E closure contains all of its contact point. Then that means what? That means by the definition of closedness, the E closure must be closed. And then we fill out this gap here. We did take an arbitrary contact point of E closure, and then we must show the contact point X must be in E closure itself. Because X is a contact point of E closure, there exists a sequence X of n such that each term of the sequence X of n is in E closure, and the sequence X of n is converging to the point X. That's by the definition of E closure. Okay? X is a contact point of E closure. So by the definition of contact point, we must have what? A sequence X of n in closure converging to that contact point X. Each X of n is in E closure, then what do you say about E X of n afterwards then? Since each X of n is in E closure, there exists some corresponding Y sub n in the subset E such that the distance between X of n and Y sub n is less than 1 over n. Okay? For all natural number n. Yeah, this is true because what? Because each X of n is in E closure. By the definition of E closure, right? There must exist some corresponding what? Element Y sub n. Okay? Such that the distance between X of n and Y sub n is less than 1 over n. Term-wise. What I mean is, each X of n is a contact point of E. That's what that means, right? Each X of n is in E closure. What does that mean? By the definition of E closure, each X of n is a contact point of E. That's what that means. So by the definition of the contact point, what must be happen? No matter what neighborhood around, no matter what, we have used 1 over n neighborhood around X of n. No matter what neighborhood around X of n we choose, there must exist some element Y sub n in E, in that neighborhood. So in this case, we have used 1 over n neighborhood around X of n. Any 1 over n neighborhood around X of n, there must exist some other element Y sub n in the subset E. Right? That's what that means. So we have two sequences X of n's and Y sub n's here. Then how do we compare those two sequences? What happens to the distance between new sequence Y sub n and the point X we have chosen? By the triangle inequality, this distance is less than or equal to distance between Y sub n and X sub n plus distance between X sub n and X. By the triangle inequality on the metric space. But the distance between X sub n and Y sub n is less than 1 over n, pointwisely, plus distance between X sub n and X. Distance between X sub n and X. Distance between X sub n and X. What happens to distance between X sub n and X? This number converges to 0 because X sub n sequence converges to X. But 1 over n converges to 0 as well. So then what happens to what? Distance between Y sub n and Y. The whole thing must converge to what? 0 as well, right? So that implies the sequence y sub n converges to the number x, the point x. I shouldn't say number. That's habitual, but I shouldn't say that. Okay? Because that's a general metric space. Yeah. So the sequence y sub n is converging to x, and each y sub n sequence is what? In the subset E, right? For all index number n. So we have a sequence in the subset E converging to x. Then what do you conclude about x? X must be what? A contact point E of E. We have a sequence y sub n in E, the subset E, converging to x. Then what does that stand for? That stands for x must be a contact point of E. In other words, x must be in E closure. By the definition. Okay? By the definition. So, no matter what contact point of E closure we have chosen, that arbitrary contact point of E closure must be what? Also in E closure itself. That was what we have justified. Which means what? E closure contains all of its contact point in. All of its contact points in. Which means by the definition of the closedness, we must conclude what? E closure must be closed. That's the second lemma about the closure. About the closure. And then let me restate the next lemma. Okay? The next lemma says, if we take any closed set containing E, then the closed set D must contain the closure of E. Closure of E. What does that stand for? If you take any closed set containing E, then what? Then the closed set D must contain the closure of E as well. But closure of E is closed, right? Closed. Then what does that stand for? That stands for what? E closure of E is the smallest closed set containing E. That's what that stands for. Does it make sense to you, right? So no matter what closed set containing E you choose, there's an arbitrary closed set containing E. No matter what closed set containing E you choose, that closed set containing what? E closure. But E closure is a what? Closed set containing E as well, right? So if we combine all three lemmas together, then what do you conclude? We conclude that what? E closure is the smallest closed set containing E. That's what we conclude if we combine all those three lemmas together. E closure is a closed set containing E, right? From the first two lemmas. But the next lemma says what? Any arbitrary closed set containing E contains E closure. So if we combine all those three lemmas together, then we conclude this here. This line over here is the combination of the three lemmas together. Then we must conclude E closure. Closure of E is the smallest closed set containing E. Smallest closed set containing E. That's what we must conclude. How do you justify this? The third lemma there. We must justify this inclusion under this condition here. Right? For the purpose, let's let X be an arbitrary element in E closure of E. Then by the definition of the closure down here, there exists a sequence X of n. Okay, X of n. Okay, in E converging to the point X. But because E is a subset of D, this sequence X of n is in D as well, right? Yeah, we actually did take a sequence X of n in E converging to X, but because E is a subset of the closed set D by the assumption, the sequence we have chosen is what? A sequence in the closed set D as well. Then what does that stand for already? We have a sequence in D converging to X. Then what does that mean? That means what? That means X. X is a contact point of D. Because X is in the closure of E, first of all, X is a contact point of E. But because E is a subset of D, right? We conclude the same point X is a contact point of D as well. Because we could choose a sequence in D converging to X. And D is closed by the assumption as well. Okay? So, what do you conclude? D is closed, and X is a contact point of that closed set D. So, by the definition of the closedness, what must happen? The contact point X must be in D as well, right? By the definition of the closedness. The closed set D must contain all of its contact points, and X is one of them, right? So the contact point X must be in the closed set D as well. So every point X in the closure of E is also in the closed set D. That was what we have justified. So that implies what? Closure of E must be a subset of the closed set D, which was what we have desired. The closure of E. So the closure of E is the smallest closed set containing E. We have a metric space, and we have some subset E. I don't know how that subset E looks like. And then there are a lot of closed sets containing E, right? There are a lot of closed sets containing E. And then E closure is the smallest closed set containing E. That's what that means. In other words, if we take any other closed set containing E and then what? Then that must contain the closed set E closure as well. That's what that means. Then you can easily write out the next lemma here. How do we rewrite the closure of E more mathematically by the previous results in this lemma? Yeah, this was the smallest closed set containing E. Then how do we rewrite it more mathematically? That's the intersection of all closed set D containing E. Does it make sense? Yeah. E closed. Closure of E is the smallest closed set containing E, right? Then how do we rewrite closure of E more mathematically? That's the intersection of all closed set D containing E. Take the intersection of all closed sets containing E. That will be what? The closure of E. That will be the closure of E. That's easily derived from the previous results. How about if the closure of E and E are identical? Then what do you conclude equivalently? The original set E and its closure are identical. Then we must conclude equivalently what? The original set E must be closed. We can easily justify the proof of that on the lemma 5 here. The forward direction is easy, right? If E and E closure are identical, then because E closure is closed by the second lemma here, E is also, right? Yeah. If E and E closure are identical, then what? Because closure of E is closed by the second lemma there, E is also closed, which is our result. That's trivial by the second lemma here. Then how do we go backwards? If E is closed, if E is closed, if E is closed, if E itself is closed by the first lemma down here, if E is closed, then by the definition of E closure, well, if E is closed, then what does that mean? Then E is one of the closed sets containing E itself. E is a closed set containing E itself, right? That's what that means. If E subset E itself is closed, then what? Then the subset E, that means the subset E is a closed set containing the subset E itself. So what then? By the definition of E closure, what must happen? Closure of E is the smallest closed set containing E, but E is a closed set containing E. Then what inclusion must be happened here? E closure must be a subset of E. Yeah, if E is closed, we have supposed, then what must be happen? Then that means E is a closed set containing E itself. But E closure of E is the smallest closed set containing E. So we must have that inclusion. The closure of E must be a subset of E. But we already know the other conclusion is true. The other inclusion is true in number 1. But by the first lemma, we must conclude what? E closure of E and E must be identical, which was what we have just derived. If we apply this lemma 5 to E closure, if we apply this lemma 5 to E closure, then we must have the following. Double closure of E must go back to what? Go back to the original set. Yeah, go back to what? Single closure of E. Apply this lemma 5 to what? Apply the lemma 5 to E closure, and then we have this, lemma 6 here. Okay. Closure of this. Okay. Yeah. That's true because closure of E is closed. The right hand side said it's closed already, right? Then what must be happen? The closure of this closure set must be itself. That's what that means. By the second lemma over here, this closure of E is closed. If then what must happen? If the right hand side set is closed, then what must happen? By the lemma 5, its closure must be itself. That's what that means. Yeah. Let's continue next week.